Hello, Charles and I are going to talk about Mosfet amplifier characteristics.
In this presentation, we'll go over the common source amplifier, the differential pair amplifier, and the transconductance amplifier. First, we're going to talk about the common source amplifier. The first task is to find the voltage gain. We have an equation for the reference current. We know Iref, I threshold, Vs, and Ut are all constant. Differentiating and substituting Vg equals Vin and Vd equals Vout, we obtain the gain of negative kappa over sigma. The small signal analysis produces the same result. Using the hybrid pi small signal model shown in the picture to the left and applying Kirchhoff's law on one of the nodes, we get an inverting gain of kappa over sigma. The question arises, would Iref affect the gain? From both the large and the small signal models, we can see that Iref drops out of the equation and does not affect the gain. It was a bias current anyway. From the previous project, we know that the equation for Iref and kappa will change for the above threshold region. Using the small signal model in the picture shown to the left, we get a gain of negative kappa I over Ut times Ro. Now we'll look at how this modifies the amplifier gain from the ideal current source model for the same bias current. The amplifier gain now depends on both the INFET and the PFET. Using the same techniques as the ideal current source, we find that the new voltage gain is kappa over sigma INFET plus sigma PFET with an inverting gain. Looking at the derived equation for the common source amplifier, we know to get the highest gain we need to make kappa as large as possible and sigma as small as possible. This graph shows the input voltage versus the output voltage for the common source amplifier. This is graphed in order to experimentally find the gain from the slope. This can be seen from the curve fit of the slope, which is the green line. The simulation data is also plotted on the graph as the red line, which matches fairly closely. Experimentally, we found the gain to be negative 359.3 from the curve fit. Using the values from the previous project, we can calculate the gain to be negative 359.15, which matches very closely to the experimental value. The ideal value would lie between negative 300 and negative 1000 for the gain.
We now move on to the differential pair amplifier. Let's analyze the differential amplifier. The differential amplifier contains two MOSFETs that produce currents I1 and I2. When we use Kirchhoff's laws on the circuit, we get that I1 plus I2 equals IB, which means that the currents are in subthreshold. Also, for the MOSFETs to be in the saturation regime in subthreshold, a minimum VDS of 4 UT is required, which is about 100 millivolts. We move on to deriving the currents I1 and I2, neglecting early effect. From a general equation for Iref and a constraint on Iref equaling I1 plus I2, we can get the equations for I1 and I2 as described below. We notice that when we assume V1 to be much lesser than V2, the currents can be simplified in terms of V2 alone.
This shows the MATLAB plots for I1, I2, I1 plus I2 on a linear and log scale. The plot on the left shows I1 versus V1 minus V2. Using the equation we have previously derived for I1 and the curve fits from the graph, we can obtain the values for kappa and Iref. Using the same procedure, we calculate Iref and kappa for I1 versus V1 minus V2. and for I1 minus I2 versus V1 minus V2. On comparing these values, we discover that kappa is about 0.74 and IREF approximates to 7.5 nanoamps. Also, these values are similar to the values in Project 1.
Moving on to the transconductance amplifier. A transconductance amplifier typically has a current mirror attached to a differential pair amplifier. This graph shows the experimental data, the simulation, and an appropriate curve fit for the IV graph of the transconductance amplifier. Let's take a moment to look at the plots of the differential amplifier and the transconductance amplifier. We notice that I out is not equal to 0 when delta V equals 0, which means that they are asymmetric and have an offset of 25. The asymmetries plus transistor mismatch can be explained by considering the current mirror. In reality, the mirror does not have 100% reflectivity, probably due to differences in I naught. Thus, this makes the current produce a mismatch in M3 and M4. As stated before, delta V does not coincide at the point where I naught equals 0. A question arises about input offsets. The input offsets to the system depend on the transistor parameters such as temperature, and they do not alter the gain or the bias voltages. The gain for a transconductance amplifier is calculated from the slope of the graph of output voltage versus input voltage. The output resistance is calculated by taking the slope of the IV curve of a transconductance amplifier. Similarly, the transconductance can be calculated by taking the slope of the IV curve of the transconductance amplifier. The gain, the output resistance, and the transconductance value seem to be closely agreeing with the calculated values.